Example 22.11 is wanting us to go in the opposite direction that we did with examples 22.8 through 22.10. Rather than expanding and evaluating, we are asked to express each sum using the summation notation. So we're trying to go back to the condensed form rather than the expanded form because we're actually starting with the expanded form here. You'll notice that we have 1 cubed plus 2 cubed plus 3 cubed plus ... 7 cubed. So it might not be unreasonable to think of these as A1, A2, A3, and then down here at the end, I would be willing to bet that that's probably A7. And I can base that off of the pattern that I see. I'm noticing that the exponent is the same in every single one of those terms. The only thing that's changing is the base. So when it comes to writing the expression as a summation notation, we're going to first draw the sigma symbol, and we're going to select a index for summation. I'm going to use I, and I'm going to start with I equals 1. And the pattern here for each one of these terms is some number cubed. So I'm going to use the index to represent the number that I'm going to be plugging in for, 1 cubed, 2 cubed, 3 cubed, so on. And then the very last number that I would want to plug in is 7. So that takes us from the expanded form back into the condensed form, known as summation notation. That's all we're looking for here. Part B is going to be very similar. With Part B, I have my A1, A2, A3, A4, and then what looks like the AN term. I don't really know. I don't have a specific value for n on this one, and so I don't really know what else to do with it, so I just call it AN. So let me start with my sigma symbol, and I'm going to pick my index again. I'm going to use I. And when we have the choice when creating the summation notation, it is preferred to start with 1 whenever possible. There is a whole host of formulas that allow summations to be done more quickly if you have your summation starting from 1. Those would be things that are addressed in other aspects of sequences that we won't get to in this section. But now it's on to the pattern here. Now, what exactly is the pattern involved in each one of these terms? So I notice that the only number here, the only term that's not a fraction is the very first term, but I can treat it like a fraction if I turn it into 1 over 1. So now they all look like fractions, and the numerator of every single one of these is a 1. It's something that is constant, not changing. So I can make all of these terms look like a fraction 1 over something. So here's the hard part. It's figuring out what exactly needs to go into the denominator for this. Now, one thing that I'll notice is that 3 would be the same as saying 3 to the first power. 9 would be 3 to the second power. 27 would be 3 to the third power. And on that first term, 1, that could actually be written as 3 to the 0 power, because I'm trying to get some kind of pattern here involved. And as it turns out, if you look here at the last term denominator, 3 raised to the n minus 1, that actually tells you your pattern right there. If you plug in a 1, you're going to end up getting 0 for the exponent. If you plug in a 2, you would end up getting a 1 for the exponent, because you're going to have to subtract 1. So the pattern here would be 3 raised to the I minus 1 for the denominator, and then the upper bound for the summation is going to be n, because that would be what we would have to plug in to get that to that very last term, an. And that is the summation notation there for part B.